I am Dr. Sudhan Sharma from School of Computers and Information Sciences, Indira Gandhi National Open University, and now this session is about matrix operations 2. In the earlier session, we learned about elementary row operations. We learned about what are different types of elementary row operation, likewise scaling, interchange, replacement, and how to apply those elementary row operations to determine the triangular matrix or to determine inverse of a matrix. Apart from this, now we are going to extend our discussion which we made in our last session, that is matrix operation 1, to this session, that is matrix operation 2, wherein we are going to explore about the understanding for the rank of a matrix. So, the objectives of this session are to determine the rank of a matrix and to understand the normal form of a matrix. Apart from this, we are going to extend our understanding of our last session to determine the inverse of a matrix by using elementary row operations. So, let us begin. What do we mean by the rank of a matrix? The formal definition of a rank of a matrix is that A be a M cross N matrix, then the order of the largest square submatrix of A whose determinant has a non-zero value is the rank of the matrix. So, rank of a 0 matrix is definitely 0. So, what does this statement mean? Let me reread this statement. The order of the largest square submatrix of A whose determinant has a non-zero value is called rank of the matrix. Let us apply the understanding of this statement into this example. Over here, we are required to find the rank of a matrix. The rank of the matrix A 0 1 minus 1, 3 1 2 and 2 4 6. So, now let us calculate the determinant of this 0 1 minus 1, 3 1 2, 2 4 6. So, first value is 0, we already learned 0, this into 6 into 1 minus 2 into 4 minus 1 into, so this is next part. So, 6 into 3 minus 2 into 2 plus 1. So, this is 3 into 4 minus 1 into 2. So, this turns out to be 0 minus 1 into 18 minus 4, 6 3 the 18 minus 4 plus minus 1 plus minus 1 into 4 3 the 12 minus 2. So, overall result turns out to be minus 24, which is not equal to 0. So, this is the largest square submatrix. So, largest square submatrix is 3 cross 3, and that is why the rank of this matrix is 3, because the entire value of this matrix, the determinant of this matrix is not equal to 0. So, that is why the rank is 3, that is why the rank is 3. We will have more clarity when we are going to solve some more examples. Let me give you one more example. Over here, we are supposed to determine the rank of a matrix. Now, if we calculate the determinant of this given matrix A, which is 1 2 3 0 1 2 2 5 8, and performing the calculation, you will find that determinant turns out to be 0. So, that means the rank of A is not 3. Now, what is the sub value if we target at this? So, that means the determinant value of this sub matrix is not 0, 1 2 5 8, determinant value of this turns out to be minus 2. So, that means rank of matrix A is 2. So, you need to, as per this definition, order of the largest square submatrix of A whose determinant has a non-zero value is called rank. So, largest square submatrix, in this case the largest square submatrix is this 1 2 5 8, that is why the rank is 2. What is the order of this largest square submatrix? This is 2 cross 2. So, that is why rank is 2. Over here the rank order was 3 cross 3 and the determinant turns out to be 0, that is why the rank of the matrix cannot be 3. So, I hope you understood what do we mean by the rank of a matrix. Now, there is a relationship between the rank of the matrix and the elementary row operations, and which is given with the help of a theorem. We are not going to prove this theorem, but it says that the rank of a matrix remain unaltered under the elementary row operations. Apart from this, there is a note that the rank of matrix can be easily identified by counting the number of non-zero rows obtained after elementary operations. That means, elementary row operations or elementary column operations, whatever. So, whatever non-zero rows are obtained after performing the elementary row operations or column operations is the rank of a matrix, and the rank of the matrix is not altered by performing the elementary row or column operation. Now, let us understand this theorem by solving one more numerical. Now, over here we have the question given to you is find the rank of the following matrix. The matrix given to you is 1, 2, 3, 2, 4, 5, 3, 6, 8. Now, performing the elementary row operation, that is R 2 is to be replaced by R 2 minus 2 times of R 1. So, performing R 2 to be 2 minus 2 times of R 1. What are R 1 values? Are 1, 2 and 3, that is 1, 2 and 3, 2 times of R 1. So, new values turns out to be new values of row 2 after performing the operation R 2 minus 2 times of R 1 turns out to be 0, 0 and 0, 0 and minus 1. So, this is the first elementary row operation. Now, after this we need to perform other elementary row operation. R 3 is to be replaced by R 3 minus 3 times of R 1. On the same line of action, what is R 3? You will get 1, 2 and 3 times of R 1. What are R 1 values? R 1 values are 1, 2 and 3. So, 1, 2 and 3, 3 times of R 1. So, R 3 minus 3 times of R 1. So, R 3 values are 3, 6 and 8. So, 3, 6 and 8. So, this is R 3 is to be replaced by R 3 minus 3 times of R 1. So, after performing this operation, what values you will get? You will get these new values, that is 0, 0 and minus 1 as R 3. Now, subsequently performing one more elementary row operation, that is R 3 is to be replaced by R 3 plus R 2, you will find that the resulting values are in this case 0 plus 0. So, this is 0 plus 0, 0 plus 0, this is 0 plus 0 and minus 1 plus minus 1, minus 1 plus minus 1. So, that means this value turns out to be plus 1. So, as a result of which this is 0. So, this is 0. That means after performing these elementary row operation, we are finding that there are 2 rows which are non-zero, as a result of which the rank of the matrix turns out to be 2. So, I hope you understood that we need to as per the note, we need to identify the number of non-zero rows obtained after the elementary row operation, and over here we are having 2 rows which are non-zero, as a result of which the rank is 2. Now, we can use the standard technique instead of performing elementary row operations, wherein the same matrix is actually examined over here, same matrix 1, 2, 3, 2, 4, 5, 3, 6, 8, which was being solved by performing elementary row operations, and by performing elementary row operations finally we identified that how many rows are non-zero, and by using this concept that the number of non-zero rows leads to the rank of a matrix. We are going to solve the same problem with a different technique, and which is already delivered to you. The same matrix 1, 2, 3, 2, 4, 5, 3, 6, 8 is given to you. We calculated the determinant of this matrix and it turns out to be 0. That means the rank cannot be equal to 3, because this determinant of order 3 cross 3 turns out to be 0. Now, the sub matrix whose determinant is not 0 is 4, 5, 6, 8, 4, 5, 6, 8. We calculated the determinant value, that turns out to be 2. Hence, the rank of the matrix is 2. So, we need to find the subdeterminant whose value is not equal to 0, and the order of that subdeterminant is in fact the rank of a matrix. So, we will apply the understanding of the concepts which we learned in our earlier session. That means, in our earlier session we learned about identity matrix, and we extend that discussion into this session, wherein we need to understand about the normal form of a matrix. Now, the formal definition of the normal form of a matrix states that an M cross N matrix of rank R is said to be in the normal form if it is of the type IR and remaining thing values are 0 in fact. So, IR is in fact the rank, of the matrix. So, that means this matrix which is given to you, this IR. So, this is I2, this is identity matrix of order 2. We learned that I2 is nothing but 1 1 0 0, and we also learned that I3 is equal to 1 1 1 0 0 0 0 0 0. So, diagonal elements are, this is a 3 cross 3 identity matrix. So, this is why it is I3. So, in the normal form will be written in this format, that is I, because rank is to I2 same R over I2, all other values are 0. We learned I2 0 value and again 0 values and 0 values. So, R is in fact the rank and N is number of columns. So, you find that this is the normal form. The normal form leads to, again if you want to represent this matrix in the normal form, then this chunk is in fact I3. So, I3 0 is nothing but the normal form of the matrix. Now, there are two theorems which are very clear, that every matrix can be reduced to the normal form by elementary operations. And the second theorem states that every matrix of rank R is equivalent to the matrix IR 0 0 0 0. So, we will learn about this normal form by the help of a numerical example. Say the example is to reduce the matrix A to the normal form by elementary operations. Now, again on the same line of actions, over here we need to understand how to bring it, how to resolve this matrix into an identity matrix. Now, performing firstly the replacement operations. So, replacement operation is performed. On the basis of replacement operation, the new identity matrix which is derived is this one. Again, no, this is not replacement operation, this is interchange operation. By performing interchange operation first, because we just recall the algorithm, we the first value should be all the values before that should be 0. So, just recall the algorithm. We first perform the interchange, then we are performing the replacement. Okay, again we are performing the replacement, So, after performing these operations, that is R3 is to be replaced by R3 minus 5 R1, we get new modified matrix A. On the same line of actions, when we are performing this operation, that is R1 is to be replaced by R1 plus R2, R3 is to be replaced by R3 minus 8 R2. You will slowly are moving towards the point wherein you are getting the identity matrix as one of the submatrix. So, this is I2 0 0 0, and this is nothing but the normal form. We already learned that by performing the elementary row operation, we learned how to transform a matrix into an identity matrix, and over here we are getting a submatrix whose value is an identity matrix, and this form of representation is nothing but a normal form. Now, again extending the concept, if we are supposed to find the rank of this matrix, then the number of non-zero rows, are 2. So, number of non-zero rows, this is the non-zero row and this is non-zero row. So, the rank of the matrix is equal to 2. And again the rank of, if we calculate the rank of a matrix, we will find that again it is 2. That means the elementary row operations, after performing elementary row operation we are getting the rank is equal to 2. But if we are not performing the elementary row operation, we are just calculating the determinant of A, and it turns out to be 0, then we find the subdeterminant determinant, and it of order 2 cross 2, which is not equal to 0, then rank is equal to 2. I hope you understand what we are trying to say. Just practice this numerical by performing the elementary row operations and the column operations. Also solve this value, this matrix by the standard procedure, which is discussed over here, that you find the determinant of this given matrix A, and this will definitely turns out to be 0. Then you are supposed to find the subdeterminant, and whose value now this is the subdeterminant whose value will not turn out to be 0, and or you just practice it, you just identify that its value will turn out to be 0 or not, then you will see that rank is equal to 2. Now, let us extend our discussion to another example wherein we identified that how this is solved by the standard procedure. This is the same matrix which we had discussed in our last example. This example, same matrix is taken over here. So, just for the better understanding, same matrix is taken over here. By solving the determinant, we find that the result is 0. So, that means rank is not equal to 3. Rank is not equal to 3. Now, the sub matrix which is over here turns out to be the top left 2 cross 2 matrix. Now, 3, this will be this into this minus this into this. So, 5 into 1 minus 3 into 0. So, this turns out to be 5 minus 0, this is 5, and this is the sub matrix, this is the sub matrix whose value is not equal to 0. So, that is why the rank is equal to 2. So, I hope you understand that by this procedure wherein we are performing the elementary row operations, we are to determine the rank of matrix. After that, we are trying to find that how many rows are non-zero. This is one of the mechanism. Second mechanism is wherein we are supposed to calculate the determinant and find the subdeterminant values wherein the result is not 0, and that order is the rank of the matrix. Now, it is very important to understand about the inverse of a matrix, how to calculate the inverse of a matrix. Inverse means if I say A divided by A, so that means A into A inverse. This will be, that means this is cancelling. So, A divided by this, so this should be equal to an identity matrix. So, A into A inverse should be equal to an identity matrix. This is very important understanding, and we are going to explore this understanding to determine the inverse of a matrix. So, we learned about identity matrix, and we learned about how to find the rank of a matrix. Now, we apply our understanding of determining the identity matrix over here to find the inverse of a matrix. So, there are some points. A is an n cross n matrix whose inverse is to be found. Then as I already said, A will be equal to identity into A, because anything multiplied by 1 is itself that value. So, A is, if I say 1 into A, that is equal to A itself. What is 1? 1 is nothing but your identity matrix. So, we need to reduce matrix A on the left hand side. On the left hand side of the equation, A is equal to In into A. So, on the left hand side, this is left hand side and this is right hand side of the equation. So, we need to reduce the matrix A on the left hand side of the identity matrix In by elementary row operations, and it might be possible that if A is invertible or non-singular, we need to check it out. We will learn about this when we are going to solve the numericals. Thereafter, we need to apply all these elementary row operations in the same order to the prefactor A, that is the right hand side of the identity, and in this way the matrix is reduced to some matrix B such that B into A is equal to an identity matrix. So, B is nothing but inverse of A. What I am actually trying to say, you will better understand when I am going to solve this numerical. So, the question over here is find the inverse of a matrix 1 1 2 3 using elementary row operation. So, as I said, A should be I into A. Since A is of the order 2 cross 2, it should be A into I 2 A. Now, what is I 2? I 2 is an identity matrix. So, this should be this, and left hand side is our A. So, this is 1 1 2 3. Now, applying the elementary row operations, that is R 2 is to be replaced by R 2 minus 2 times of R 1. So, R 2 is to be replaced by 2 times of R 1. So, this turns out to be minus 2, and again 2 times of R 1. So, R 2 should be, this turns out to be 1. So, after applying this replacement, what is R 1 value? Say over here, let me solve it for you. R 2, this is a new value of R 2. Let me solve it for you. Now, R 1 value is 1. This is the R 1 value, this is R 1 value. So, first value component 1, 2 times of R 1 minus, what is R 2 value? R 2 value is 0. So, this is to be new value of R 2. So, what is this turns out to be? This turns out to be minus 2. So, this is minus 2. On the same lines, you will calculate it to be 1. So, after applying the second replacement procedure, that is R 1 is to be replaced by R 1 minus R 2, you will get the new values this. But mind it, after performing this replacement operation, what is happening at the left hand side? You are transforming this into this. By performing next replacement operation, you are transforming this into this, and this is nothing but your identity matrix. So, B, so this is B matrix, this is A matrix. So, that means B into A is equal to identity matrix. That means B is equal to inverse of A. What you are supposed to do, simply try to apply the elementary row operations so that the left hand side of the equation turns out to be identity matrix. Once it turns out to be identity matrix, you can easily say that B into A is nothing but an identity matrix, as a result of which, because B into A turns out to be an identity matrix. So, that means A should be 1 by B. Okay? That is, B is nothing but A inverse. B is nothing but A inverse, or you can say that B is equal to 1 by A or equal to A inverse, because then only you can say B into A will be equal to A inverse into A. A inverse A into A means A divided by A, which is nothing but 1, that is identity matrix. So, you are supposed to perform elementary row operations so that left hand side transforms to an identity matrix, and then you can when after performing this transformation, whatever matrix you are getting it onto right hand side, this will work as matrix B, which is nothing but inverse of A. I hope you understand. But for better understanding, you are supposed to solve this numerical on your own, and then only you will understand what is B and how we transform and got the inverse value of the matrix using elementary row operations. Now, there is one more example on the same lines, because in the earlier example what we had done, we had solved a simpler question of wherein the matrix is of order 2 cross 2, but over here if we are going to solve it for order 3 cross 3, then again on the same lines of action, what we are doing over here, we are transforming, we are writing A is equal to, we are transforming this value, we are transforming C over here, transforming by using elementary row operations, so that we finally got the identity matrix. Now, when we got the final identity matrix, applying the same elementary row operations which are listed over here onto the left hand side and also onto the right hand side. You are transforming right hand side into this manner, and finally, you arrive at this value, and this turns out to be matrix B. So, B into A is again identity matrix. So, that means B is equal to A inverse. So, this is the inverse of A. So, by performing the elementary row operations, you are actually transforming the given matrix into an identity matrix, so that this identity is resolved, and by using this you are going to calculate the inverse of a matrix. I hope you are able to understand this. There is one more example, and this is for better understanding of yours, because over here we need to understand that if a matrix cannot be reduced in an identity matrix, then inverse of that matrix does not exist. Now, how we can solve this? That say we are given a matrix A, and we are again going to write it into the form A into I3A, and now we are performing the elementary row operations so as to transform into the identity matrix, but we find that there is an entire row which turns out to be 0, as a result of which this left hand side cannot be reduced into an identity matrix, and since A cannot be reduced to an identity matrix, that means matrix A is non-invertible. That means it cannot be inverted. So, inverse of such type is not existing. I hope you understood this thing, that by performing elementary row operations, we are going to transform it into an identity matrix, and once this expression is achieved by performing elementary row operation, you can always say matrix B is nothing but inverse of A. And so, I hope you learned the calculation part of inverse of matrix. This is very important also from the examination point of view. Apart from this, in this session you learned about how to determine the normal form of a matrix, and different ways to calculate the rank of a matrix. I hope you enjoyed this session, but you will further enjoy if you are going to apply the concepts which you learned in this session by practicing more and more in a pen and paper mode, and thank you very much.